Chris Maloney, Managing Director of the U.S. Operations at VPI Photonics, and I'm joined by my colleagues Nebras and Ilias. And today we're going to be discussing simulating different Datacom, Telecom scenarios in compliance with some of the emerging 800G and 1.6T standards. So first, I really want to just set the stage, explain why we're here talking about optical standards and why simulations are so important. So really, standards are necessary to ensure interoperability, reliability, scalability, as well as for ensuring smooth transitions towards future solutions. So they're jointly defined by network operators, equipment vendors, as well as individual contributors to ensure some minimum level of quality and performance. And they also help to reduce costs and risks when developing new technologies. And then also enable equipment and different manufacturers really to work seamlessly together. So there are a number of standards groups and multi-source agreements, or MSAs, that you should be aware of, in particular IEEE, IEC, ISO, ITU, and OIF. And then just oftentimes these standards are agreed to, but beforehand, usually there's some multi-source agreement that takes place. And that is an initial agreement really to ensure some level of interoperability and having some agreement among the vendors. So just for reference, you can see an example schematic below based on the OIF 400G ZR standard in the bottom right there, which you'll be seeing in a little bit more detail later on. And I know there are many of you in this tutorial who contribute to standards working groups and already know all of the abbreviations that I'm already starting to talk about. But for those of you who are a little bit more new to this, let's take a step back and just review some of the basics. So if we look at the basic architecture of a data center network, there's a number of nodes that need to be connected together, typically by optical fibers. So that means you can be connecting servers, racks, switches, all within the data center, or connecting buildings on a campus, connecting the campuses together. And each one of these links has its own unique and different requirements, both all for like data rates, length, cost. So actually, when you hear things like 400G, 800G, 1.6T, that's referring to the data rate. And then the abbreviations like ZR, ER, LR, those are referring to the typical link length of the fibers. So if you start with ZR, typically means between 80 and 120 kilometers and is referred to as beyond extended reach. Now, you might also be asking, well, what do all these abbreviations actually stand for? Well, some correspond to some commonly used terms like SR for short reach, LR for long reach, ER extended reach. But there's no real agreed to terms for all of these abbreviations. So maybe we need a standards committee for this as well. But so for example, ZR I mentioned is beyond extended reach, but also people refer to it as zero dispersion reach. FR is referred to as far reach, sometimes fiber reach, DR, direct reach, data center reach. So the main point here is that if you see one of these abbreviations, it usually corresponds to a typical link length or reach that we're discussing. So that's the main thing just to keep in mind. Now, as technologies evolve, we continue to need faster speeds, larger densities to meet bandwidth requirements. So really driven by some applications more recently as like AI, but also video streaming, cloud computing, and more. So how do we keep up with those increasing traffic demands? So there's a few ways. So increasing the bit rate is an obvious way to do that, but it also has some fundamental limitations on switching speeds. So we can also use techniques like parallelization, so increasing the number of cores, fibers, or wavelengths. We're also increasing the number of bits per symbol by using higher order modulation formats. So one of the, we'll say, most basic and obvious formats is on-off keying, where we modulate the intensity of a laser to be on and off, transmitting a 1 or a 0. So the baud rate or the symbol rate, is equivalent to the bit rate. The next level up from that would be using PAM or pulsed amplitude modulation, where a PAM4 signal has 4 amplitude levels to encode 2 bits of information on each level. So that could be a 00, 01, 10, 11. And in this case, the bit rate is twice the symbol rate because we're encoding 2 bits of symbol, 2 bits of data on each symbol. And then lastly, we'll talk about QAM, or quadrature amplitude modulation, where we leverage now both phase and amplitude. And in the case of 16 QAM, we now basically have the option to transmit 4 different PAM4 signals, but each one corresponding to a different phase. So that enables us to encode 4 bits of information per symbol. So 100 gigabaud for our symbol rate would allow us to transmit 400 gigabits per second of data. And so now you can start to think, okay, it can get pretty complicated combining these different modulation formats with different forms of parallelization. There's different equalization strategies. So really that's where simulations come in. So simulation solutions are really required for you to optimize and ensure compliance to standards using these complex technologies. So at this point, let me just walk you through the outline today. I'm in the middle of the background and motivation right now, but soon we'll be getting into running some simulations that are compliant with standards. Now, you might notice some of the technologies that we're going to be talking about today are actually emerging standards, and so the standards aren't yet agreed to. Some of those today, we're going to start off with intensity modulation and direct detection. So Nebraska will get us started around walking through an 800G FR4 example. Now this one's based on the 800G pluggable MSA, and it's an emerging standard that's currently in an IEEE 802.3 task force. And I believe the first draft for that was just recently released. We're also going to talk about 400G SR 4.2, which has an IEEE ISO IEC standard in place that we'll be referencing. And then we'll move into coherent systems, where Ilias will join us, talk about 400G ZR based on the OIF 400ZR optical specs. And then we'll talk about the 1.6T ZR, which is an emerging standard. And this will be based on that 400G ZR example with some proposals that have been made for these solutions. So before we get into the technical discussion, I'll just give a little bit of background about VPI Photonics so you know who we are and our background. But we've been providing photonic design automation software, so simulation software, for over 25 years. Our headquarters is in Berlin, Germany. That's where Ilias is joining us from today. Our US office is in Rochester, New York, which is where I'm sitting. And the 3 terms that you see in front of you here, this is how we like to describe our software. So at first, it's integrated. So we've developed all of our software solutions in-house ourselves, and we really focus on the fact that they should be integrated together. So we're going to talk about optical transmission systems today, but if you're working in silicon photonics, our photonic integrated circuit simulation software, it exists in the same user interface, same design environment. So you can easily go between simulations at different levels of abstraction. The software is also interoperable. So our software can often be the glue that holds your design workflow together, as we have interfaces and co-simulation with Python, MATLAB, C++. We also partner with a number of other software vendors. So for example, we partner with Keysight. So you can actually call the VPI software directly from Keysight ADS and use it as a building block and have a full electrical optical co-simulation and co-design. And then lastly, we claim to be industry leading. So here today, we're talking about emerging standards that are supported in our software, but also we just released a new version of our software, VPI Design Suite version 11.5. You'll find some information about that in the resources. There's a link to all the release notes about that. So you can also see we get involved in other topics like silicon photonics, laser SATCOM, And we get involved in a lot of European Commission sponsored research projects. And so we build what we learn from that directly into the software. So then you have access to it. In regards to our software solutions, we have a pretty comprehensive suite of tools that all cover different levels of abstraction. The very top is link engineering for designing and laying out full fiber networks. So those could be core, metro, PON networks. So internet service providers, equipment vendors operate at that level. Today, we're really going to be focusing on transmission design, so system level simulation tools where we cover applications, so short reach applications that we'll be talking about today, but also ultra long haul, free space optical applications, so for laser SATCOM, for LiDAR. Also, we get into radio over fiber, so a wide range of applications there. And then we can move down into component design, which is outside of the scope of today, but this is more for physical modeling for fiber amplifiers and fiber lasers, but also for photonic integrated circuits. And we do support some foundry PDKs at that level. And lastly, we even get into device simulation. So designing integrated photonic devices, fibers, so studying the different geometries, materials that are used. And so all of these tools can actually be used together. So today, I mentioned we're going to be working in VPI Photonics Design Suite, and specifically VPI Transmission Maker Optical Systems. So just to make you aware, also at this level, we have VPI Lab Expert, which allows you to connect your simulations directly to lab equipment. We have a DSP library for digital signal processing algorithms. We support quantum key distribution systems in this tool as well. And more recently, we released a VPI toolkit for machine learning. So you can actually implement your own neural network model into the software or use it for enhanced equalization for optical communication systems. So with that, I'm going to turn things over to Nebras, who's going to jump into the software and talk about some intensity modulation in direct-to-text systems.
Thank you, Chris, and welcome everyone to this webinar. Okay, so in this part, I'm going to discuss two application examples, and I'm going to start with as Chris mentioned, the first example is an 800G FR4, and that's based on the 800G pluggable MSA technical specification. So in this technical specification, the modulation format is PAM4. The baud rate is 112.5 gigabaud, and this is based on a transmission over a single mode fiber. The transmission distance is 2 kilometers. As the name implies, with FR4, we have 4 channels, 4 lanes, and we're doing wavelength division multiplexing. So we see here at the transmitter side, we have 4 transmitters, and we multiplex the signals using this mux or multiplexer. And this technical specification is also enhanced with FEC or forward error correction. So we see at the receiver side, we see this FEC decoder. And I'm going to talk more about this now after explaining the structure of the transmitter. Here at the transmitter side, we see 4 transmitters and to meet the FR4. So as the name implies, as I said, this is the multiplexer that I was talking about. And this is the FEC decoder at the receiver side. So I was just about to go inside the PAM transmitter. So I just right click on it and go to look inside. So you see how this PAM transmitter is built. So here, this is the output of the transmitter. We see here we find the PAM4, the optical PAM4 signal. And as Chris mentioned, so PAM4 compared to non-return to 0 or on-off keying, in this case, we encode 2 bits per symbol, and this has the symbol rate and signal bandwidth for a given bit rate. However, this makes the signal more susceptible to noise and device nonlinearities. So this, as you see, this transmitter is based on external modulation. So we have here an electro-absorption modulator. And if we look at the driving signal here, the electrical signal is coming from this electrical PAM transmitter. So this module generates the electrical band signal. That is, then we do signal scaling, and then a bandwidth limitation. We apply some bandwidth limitation using this electrical filter module, and then we drive this electro absorption modulator. The light is coming from this CW source, or continuous wave source. So if we look at the parameters, this generates the CW light with a specific emission frequency, average power, also line width, the relative intensity noise is included, side mode saturation ratio, etc. All these effects. We can also go one level in and see how this optical PAM transmitter is built. Now we see where the FEC is happening. So if we look inside, we see the sequence of symbols generated using this pseudo-random symbol sequence generator, and then we have this FEC encoder. And the way this works is that what the FEC encoder does is to redundant information to the transmitted signal, and so these redundant information are used at the receiver side to correct for bits. So they are removed or used by the decoder at the receiver side to correct for errors. Then we do signal mapping, symbol mapping here, and then this module is based on co-simulation. So it uses this Python code to do pulse shaping, adding jitter, and other effects. Transition time, for example, to make the signal more realistic. If we go back to the main schematic, so we were inside this transmitter. And by the way, if we look at the parameters of this transmitter, we see that we can control the parameters of all the modules inside from here. We don't need to go inside to control the parameters. So we see here the parameters for FEC, for PRDS, pulse shaping, etc. And we see for FEC, we can see the code types which are supported by this transmitter, by the FEC encoder, basically. So in this case, we are doing Reed-Solomon. As per the standard, this is the outer code. You can, in this case, we're just doing an outer code, but we can also do concatenated FEC. So we can add, for example, DCH to the as an inner code. And that's by adding another encoder at the transmitter, adding another decoder at the receiver. That's quite straightforward to implement. While I continue doing this, I'm going to run this sweep here, and what this sweep does is to change or to vary the transmitter bandwidth here. So that controls the bandwidth of the that electrical filter at that comes right before the modulator. So here I'm going to open this sweep, and you see it's going to vary the transmitter bandwidth between 50 gigahertz up to 70 gigahertz in this case. And I'm using parallel sweeps in this case to make the simulation faster, and we keep it down while it runs. I continue explaining the schematic. So after multiplexing the four signals here coming out from the transmitters, we transmit the signal to this single mode fiber, and this fiber accounts for attenuation, chromatic dispersion, kernel linearities, cell phase modulation, cross-phase modulation, etc. All these effects. We have here an optical filter that mimics the demultiplexer at the receiver side. So here you can include the transfer function of the filter. Here is approximated as being Gaussian. It's a bandpass filter apparently, but you can upload your own measured filter that describes the actual demultiplexer transfer function. So you can then take your measurements into your measurement result into a file and use that to describe the transfer function of this filter. We do then detect the signal using this photodiode, and this here we consider a specific responsivity. We got thermal noise, shock noise. Then we do bandwidth limitation. So this electrical filter represents the bandwidth limitation of this photodiode. Then after clock recovery, we do BER estimation. In this case, we see, so this module is capable of doing BER estimation, different methods, statistical methods, or Monte Carlo. In this case, we are doing Monte Carlo simulation, which means direct error counting of bits for the bits. And then comes the FEC decoder, as we see. This is also, here we see that we selected the Solomon as similar to the transmitter side, to the encoder in the transmitter, and then we count errors again. The purpose here is to compare the BER before and after FEC to examine the performance of FEC in this case. We have here several signal analyzers connected at different points. These are universal analyzers which help you to visualize the optical or electrical signal. So this analyzer shows the electrical signal, whereas this one shows the optical signal at the output. So let's look at the results. We have them already. Because I'm doing parallel simulation or parallel sweeps, which uses the different logical processors on my machine. It's just a normal laptop, by the way. It finished in less than 2 minutes. We see here at the this plot shows the spectra for the 4 lanes. They are separate by 20 nanometers. We can use markers to verify that and see. And so marker A and marker B, and we see the marker reading here, by the way. We see here, this is one of the signals. So using that filter, we selected one of the channels. So that's channel number 3. And I can, by the way, copy the trace and from this plot, paste it here. And then if we remove this marker, we can then see the effect of filtering, as you see, of that optical filter. Here we see the eye diagram before estimating BER. And you see that we can, because we are doing a sweep, so we can choose a specific iteration. So this iteration corresponds to the bandwidth of 50 gigahertz. And then we can navigate to and look at the other values, navigate through them. 50, that's 65. Sorry, the last one is 70 gigahertz, and we see a larger eye opening here. And here we see the BER results. So BER versus transmitter bandwidth. And we see that we have pre-FEC and post-FEC. So in blue, that's pre-FEC. Can maximize this. And what happens here with FEC is that if the BER is under the FEC threshold, then you get error-free performance, because that's Monte Carlo. And we can, by the way, switch to text view in this case to see the results more clearly. And we see that here we have transmitter bandwidth. And when the BER before FEC is above the threshold of 1e⁻3, then the FEC cannot help. Whereas for the other cases where we have a BER under the FEC threshold, then we have error-free performance. Okay. So now let's move to the next application example. And so that's here. And that's based on the 400G base SR42. This standard was already out in 2021. It is the reference for it. It's based on a multimode fiber transmission. The transmission distance is 150 meters using OM5 fiber. So other distances correspond to other types of fibers in this standard. The baud rate is 26.56 gigabaud, and so this gives you around a 50 gigabit per second per channel. And in this case, we are doing transmission or simulating 2 channels for 2 wavelengths as supported by in this standard, the SR42, the 850 nanometers and 910 nanometers. So you see here we have also the modulation format is FAB4. We have the 2 transmitters, the 2 different the 2 different wavelengths are specified using these 2 lasers. And you see one main difference here compared to the previous application example is that we are doing direct modulation instead of external modulation. So this model here is for a multimode VCSEL. And we see here, if we check the parameters for this VCSEL, we see the model is pretty physical here. And you see the device structure, the active region, dimensions, optical parameters, such as the confinement factor, the reflectivities of the mirrors, gain parameters, carrier dynamics parameters. Thermal effects are also included. We see here we are modeling the parasitic effects. So this can be described as a basic circuit or full circuit. And we can see what this means by looking at the module reference. So we have pretty comprehensive documentation, and we can see the the reference for this module, for this VCSEL. And you see that what that basic circuit and more advanced circuit mean. Or full circuit. So this is for the full circuit, and the model for the full circuit for the parasitic effect, and this is for the basic circuit. You can see here also the equations, the theory for the VCSEL itself, and if we scroll down at the end, we see the references for this. All right, so if we go back here, also for the VCSEL, you need to worry about the biasing and the modulation. So that's all set here by this transmitter. So we select that, and it's a global parameter in this case. So the biasing of the VCSEL is 10 milliamps. The modulation amplitude is 6 milliamps. And for more information, you can refer to this paper about this specific example. Here we are doing also, we have the multimode fiber, and we have a multimode coupler to just model the coupling between the VCSEL and the fiber. We're multiplexing the two channels here. We're doing transmission over two branches. One is 150 meters, and the other one is just 1 meter to represent the back-to-back case, but in the same time, keeping the effect of coupling with the coupler. Here we have the receiver. At the receiver side, we can look inside for the stamp receiver and see, again, we have a photodiode, bandwidth limitation. And then one major difference here is that we're doing BR estimation using statistical method rather than Monte Carlo. This uses the PDX of the received signal. Also, let me run this. And if we look at the parameters here of the VCSEL, so we see that we have 4 modes for the VCSELs that we are simulating, and here we specify the frequencies of these modes, and I think the results will start now to show soon. This takes also just 1 minute to run with the specified number of the symbols being simulated. And as you see also, these models, like for the multimode fiber and for the multimode VCSEL, we have these solvers, which work with together with these modules of the multimode fiber. And the multimode fiber here, in addition to attenuation, it accounts for the dispersion effects, including modal dispersion, as well as chromatic dispersion. So if we go here, we start to see the results, and these are the spectra for the signals for the two cases, or the two wavelengths, 850 range and the 910 nanometers. You can here in the control panel, you can control, we switch to the common settings. We can control which mode are being shown here, displayed. So you can control that right away. You can control the number of modes as well. And we see that also the eye diagrams started to show. And these are the eye diagrams we see here, we have one eye diagram that represents the case of back-to-back. So like at the transmitter side, and this is the eye diagram after transmission. We also have the SER versus fiber length. So one can do a sweep, for example. And in this case, we have good eye openings, but if you do, one can then explore the limitation here. By 300 meters, then one can see the effect of transmitting over that larger distance. And we see for the eye diagram, you can just referring to the requirements, to the specifications itself in the standard, we can analyze this eye diagram and look at metrics such as the optical modulation outer, for example. You can look at that directly here. Also the the eye height 6 for the different eye openings, and this kind of also the means for the different levels of the PAM signal. You can also look at the timing analysis, also to comply and make sure that they comply with the standard, looking at the transition, the rise fall time, for example, and so on. Also, we have here the SER, as I mentioned, for the two wavelengths, and this is based on, again, the statistical estimation of the SER. All right, so this was again another PAM4 example. The two examples are based on intensity modulation direct detection, and now I think it's a good point now to do it transition to coherent detection, and for that, Elias is going to tell you more exciting things. So let me stop sharing, and Elias, the floor is yours.
Thank you, Nebras. Thank you very much. So now Nebras discussed about state-of-the-art PAM for direct detected systems. And the focus now of this presentation will be to demonstrate coherent systems for short reach. So for instance, connecting data centers. And this will be based on the agreed ZR commercial technology as previously discussed by Chris. So in ZR, we use quadrature amplitude modulation, QAM formats, as we can see in the diagram here. And in DPI photonics QAM transmitter, we offer various options to increase the bit rate. One of them is increasing the symbol rate, which is essentially the baud rate. And we can directly do it from the schematic global parameters here. We have specifically set it to this number in order to get 400G per channel ZR, as recommended by the OIF standard, which also you can check in the references here. Now we can also increase very flexibly the bits per symbol, which essentially will increase the modulation format order and the constellation size. So again, we can do that through the schematic parameters. And since we're going to work with dual polarization, 16 QAM, we're going to use 4 bits per symbol. Finally, we can also increase the number of channels or carriers. And here in this application, we work with dense wavelength division multiplexing. So we're going to work with 3 channels as recommended in the standard. So we need just 3 galaxies. So each galaxy is the same one, so we just replicate it. And inside the galaxy, we can see the dual polarization QAM transmitter, how it has been implemented. So we modulate independently for X and Y polarization. And then with the help of the PBS here and a common CW laser, we can maintain them orthogonal. Mach-Zehnder modulators are placed in order to modulate for the in-phase and quadrature components. We have now the channel spacing has been agreed at 75 gigahertz. So the center one, we place it as mentioned here in the global parameters 193.7 terahertz. And so all we need is to put a minus 75 gigahertz for the lower frequency channel, and for the higher one, plus 75 gigahertz. The channel under test is the middle one because that will suffer the most from nonlinear crosstalk effect after fiber transmission. In order to make it even more a realistic simulation, we have added the skews here for X and Y polarization, which basically adds delay of I with respect to Q driver signal for X branch and Y branch respectively. We have also added IQ phasing balance, again for the 2 branches. So then after this, we multiplex the 3 signals, and then we oversample, and then we use an optical amplifier to set it at a specific power level. So for 80 kilometers transmission, we need very high power here at 13 dBm, but of course, this is something you can optimize. At the receiver side, for the middle channel, we use an optical bandpass filter, and then we have another galaxy at the coherent receiver, which if we look inside, is a polarization diversity receiver with point photodiodes and filter limitations. And we are using realistic ADCs. Notice we have 2 outputs here at the end. So this corresponds the upper arm to the actual sample signal, while the lower arm is the sampling rate from the ADC. And so very easily we can connect it now to the DSP unit. So the whole DSP unit is constructed by the DSP library. So the DSP library, if I open it, you can choose the algorithm you wish. And we can see each algorithm we choose is to compensate for a different type of distortion. But we have to connect, all the algorithms are interconnected to each other. So essentially we have cascaded DSP libraries here. So keep note to go to the module reference, because if you scroll down about the middle here, we have a very nice table showing a very big collection of algorithms. And just with a click of a button, for example, for CD compensation, you can see the description of the algorithm and also the respective reference. So after chromatic dispersion compensation, you can see also the related parameters that are taken from the fiber we have selected. Then we have the Stokes space rotation algorithm, which will code for the random birefringence. Then we have a time domain equalizer, which is adaptive using the multimodulus algorithm in order to compensate polarization mode dispersion. In addition, inside here, we have a 2x2 MIMO, a multiple input, multiple output, in order to extract, to demultiplex the X and Y tributaries, the X and Y branches. All these three algorithms work at 2 samples per symbol. So then we need to downsample to tackle the transceiver effects now at 1 sample per symbol. As you can see, I have deactivated these two modules. So let me run it first without activating them. And we want to see now the impact of the frequency offset and the phase noise from the lasers. So yes, essentially the carrier frequency recovery now here, without the carrier frequency recovery, we will still be able to see very large symbol rotation. So everything is rotated, and so demodulation is impossible for both polarizations. So I'm going to keep X polarization for comparison for later on. You can see there is no there's no demodulation here. Here we can also see the 3 transmitted optical channels. Now let me rerun the system, but this time I will activate this algorithm. So this algorithm, the carrier frequency offset compensation, it happens because the transmitter laser operates at slightly different frequency compared to the receiver laser, which is the local oscillator. And so what we will see now is still some symbol rotations, and that will be exclusively due to the phase noise. And this is what is remarkable with VPI photonics, is we can switch on off different algorithms, and you can easily inspect the spectrum, the electrical spectrum, the optical, the constellation diagram, and the bit error rate. So let's see here the result. So we can see smaller rotations indeed. So let me take it next to that. So you can see some improvement, but because the line width is quite high, we still have very high rotations. So in the final step, I will activate the last algorithm for carrier phase recovery, and at the same time, I will run a sweep here located at the resources folder, which is the bandwidth versus the bit error rate. This is the S21 bandwidth, which initially was set at 40 gigahertz. And now the task is to find the minimum required bandwidth in order to satisfy here the standard concatenated forwarder correction threshold, which is 1.25 E minus 2. Also to note is that at the end of the DSP unit, we used a synchronizer DSP that not only synchronizes with transmitter, but also recovers for potential polarization swapping. And this is the dedicated BR metrics you can use. We can choose singular rate, Gaussian, EVM, and so on. So here we have chosen the bit error rate Monte Carlo, and with these functional blocks, we can average them. So we add them and divide it by 2. And this is actually the bit error rate average that you see. So the sweep have finished, and we can see also here, it's one, we can change also at the bottom on the simulation run. So the second one, we can see, first of all, that we completely demodulate the signal properly for the 16 QAM using the carrier phase recovery. And the selected modulated bandwidth, the minimum one, in order to have low complexity and energy efficiency, should be at 31 gigahertz, above which corresponds to very degraded performance above the CFEC threshold. And so, yes, I have finished this demo for 400 ZR channels. And now I'm going to change, to the next presentation. And this setup is similar to the 400G ZR, but we consider a 1.6 terabit ZR super channel solution. So this is for all channels together. We call them super channels. And the next, the envisioned standard is to carry 1.6 terabit. So this is an envisioned solution. So potentially this might change, but according to the OIF standards, one good solution might be to just add an extra channel. So we still can work with dual polarization 16 QAM and the same baud rate, but we will add another channel. And this is what VPI Photonics is showcasing, that very easily you can work on standards and make your own standards much faster. So for this case, because it's it's a high demanding system, because at 80 kilometers we add an extra channel and we have more nonlinear crosstalk effects. It has been recommended to use pilot-aided frequency and phase recovery, and also data-aided time domain equalization. So we test here the second channel, and in addition, to make it even more realistic, we have added at the receiver some imbalances, phase imbalance IQ for X polarization, and insertion loss. And for this region, as you can see, the DSP unit is more advanced. We have added another algorithm for IQ imbalance correction. Also, we have added a large realistic clock frequency mismatch of 500 megahertz, which is simply added at the receiver ADC here at the sampling rate. And in order to compensate for that, we use a more advanced clock recovery based on the Garden clock recovery at 2 samples per symbol. The transmitted power, initially we set it at 6 dBm, but one task here, what would be interesting to see is the impact of the launch optical power on the system performance. So I'm going to run this sweep, but it will take a while. So I will describe to you now how we use pilot-aided DSP in the second channel. Well, for that reason, we have a module which is called pilot symbols under. And if we see in the manual, we have different options. So in our system, we have used the insert mode replace. And in this one, we just replace some payload symbols with pilot symbols. So we sacrifice, in essence, some of them, but we don't change the sequence length. If there is another mode, also the add mode, and in this one, we don't change, we don't touch essentially the payload symbol, and so we add symbols in between. And the second case is perfect when you want to work with external forward error correction modules, similar to the one Nebra shown previously in the PAM4 systems. Regarding the pilot allocation, we have 2 different cases. So the one is with training data, and training data are essentially accumulated pilot symbols, and then in frequency domain, we just space them apart. But we have the option also, together with the training data, to have single space pilots and also make them properly spaced apart. So because we use 2 algorithms here for frequency offset compensation and phase recovery with pilots, we will use this case. So for that reason, the pilot-aided carrier frequency recovery has to work in 2 samples per symbol, and it uses accumulated pilot symbols. And that's why we put it now before the adaptive time domain equalizer. So all these are 2 samples per symbol, and decimate is yes now, meaning that we downsample now to the 1 sample per symbol, where we're going to use the pilot-aided carrier phase recovery with the single pilots, which can work at one sample per symbol. And then in the final block, we just remove all the pilots here And then again, we have the bit error rate Monte Carlo and the average of them. So let's see now what we can observe from the sweep. First of all, let's see the super channel optical spectrum of the 4 channels. Notice that the second channel has slightly higher carrier to signal ratio. This is because this channel works with pilot aided DSP, but not the other ones. And also now let's check the evolution of the curve of the lens optical power over increasing values. So we can see with higher lens optical power, the bit error rate is degraded. This is because of the nonlinear crosstalk effects from the fiber, from carrier-reduced fiber nonlinear crosstalk effects, such as cross-phase modulation and for-wave mixing, and also use of phase modulation at the same time. And so, yeah, this is something you will need to optimize when you want to define the standard on this end-user solution. And yes, so I finished also with this demo, and I covered this the data applications we have. So now I will turn over back to Chris.
Yes, thank you, Ilias, and thank you, Nebras. So yeah, appreciate those demos. Then just to summarize, standards are really needed to ensure interoperability, reliability, and scalability, as well as for ensuring smooth transitions to future solutions, which we actually just demonstrated. So we showed this within VPI Transmission Maker optical systems, which it really enables you to automate the design and analysis processes to comply with the new standards. So there's flexible simulation and analysis tools, hundreds of examples to start from. We just saw a few, and there's a wide range of functionality included, including equalization, forward error correction, DSP,